Okay, this is your stats sensei, Mr. Spensei, and this is going to be scenario 2 for the quiz. You may want to play this on a higher speed to get through it a little faster. So steel parts are heated in a large industrial ovens and tempering process prior to being installed in heavy equipment. After the parts are heated, the number of defects per part are noted for quality purposes. An industrial oven manufacturer claims their oven reduces, that's important, the number of defects per part due to their new design. As a consequence of that claim, a heavy manufacturing company is considering purchasing new ovens to replace their current ovens in order to reduce the number of defects in parts per steel. Uh, the heavy equipment manufacturing company runs a study to compare the number of defects produced by the two ovens. 250 parts were available for the study and were randomly assigned. This is important. Randomly assignment tells me that I'm working with an experiment. Remember, if it's as an experiment, it can also show causation. And were assigned by coin flip to the ovens. The results of the study are summarized in the table below. We have our current oven, and then we have the new oven. We have the number of defects for each, and we have the standard deviation. Determine at the 5% level whether or not the number of industrial oven manufacturers claim are accurate. So, the very first thing, we have to write our parameters. Mu1 equals the true population mean number of defects for the current oven. Some people might want to use MC for mu current, and that's fine. Let mu2 equal the true population mean number of defects for the new oven, in which case you could have used mu n. All right? The null hypothesis will always be equal, so mu1 equals mu2. And in our case, we're saying the mu current has greater defects than the new one. Conditions. Random assignment was given for both, and it was done by coin flip. Remember, if you say random sample, that's wrong if it's assignment. If it's an observational study, it's random sample. So if it's a survey, random sample, but if it's an experiment, it's random assignment. So it was given for both, so we're taken care of. The two samples are independent, reasonable to assume that the number of defects in the current oven should not impact the number of defects in the new oven. That's a pretty reasonable assumption. The N is less than 10%. N equals 125 for both samples. We divide by that, and we get 1,250. Safe to assume that there are at least 1,250 parts for both ovens. The sample size is less than 10% of the population. However, this is an experiment. Because it's an experiment, that should not have been included. All right? But I wanted to show it to you just to remind you the N is less than 10%. Don't forget about it, but if it's an experiment, don't include it. Normality condition. N equals 125 for both samples and is greater than 30. Both samples distribution of means. The sample distribution of the means for both are approximately normal by central limit theorem. So we now address the conditions, so we're ready to run our hypothesis test. So our formula is x bar 1 minus x bar 2, s1 squared plus over s1 squared over n1 plus s2 squared over n2. So I've taken a moment and I go back and I go, all right, I need to input the data. So stat test, and it's a two sample t-test. Oh, two sample t-test on the calculator. I probably should write that down. I need to label what it is that I'm running. So I'm going to take a moment and I'm going to write that here. Two sample t-test. So there's my label. I've told the people what it is, two sample t-test. I press enter and I have 33.56 for the mean number of defects. Scoot that up a little bit, see if that shows up better. 33.56. And then I have 5.2 for my standard deviation, and I have my sample size of 125. Then I have 32.44 for the new oven with a standard deviation of 3.78 and a sample size of 125. And my alternative hypothesis had a greater than. So I'm going to go ahead and start plugging that information in to my formula. So I have 33.56 minus 32.44. And over here, the square root of 5.2 squared over 125 plus 3.78 squared over 125. And now we're going to cross out that just in case we have an error. And I'm going to go ahead and run this thing. We never pool. When I do that, I get a probability that T is greater than 1.947, and that equals 0.0263. This is my p-value. So let's take a moment and let's go look at this. Well, my t statistic is 1.947. And my p-value is 0.02. Oops, that did not work very well. This area right here is 0.0263. That's my p-value. And alpha equals 0.05. So 0.0263 is less than 0.05. So our decision is to reject. When things go wrong in the day, and believe me, today's had multiple tests to run and multiple videos to get this done, and I still run into more problems. The ink pen just ran out. So reject the null. Okay, so we rejected the null. And so once we've made that decision, we can drop down. We can drop down and state our conclusion. Our p-value is, well, we said that our p-value is 0.0263. We reject the null. There is sufficient evidence at an alpha equal 0.05 to suggest that the true population mean number of defects for the current oven is greater than the new oven. We need to determine whether or not the oven manufacturer's claim are accurate. All right? So we need to make sure we answer that question. It appears that the claim is accurate and that the new oven produces fewer defects than the current. All right. So I've made sure I've addressed the question that they asked. All right. And we did that by proving the hypothesis test. All right. The next part says, explain the p-value in the context of the study. Well, we always need to give a definition. In this case, the definition of p-value is the probability that we get a test statistic this extreme or more extreme given that the null is true. Then we have to put it in context. In this case, there's a 2.6% chance that we would get a test statistic this extreme in favor of the mean number of defects being greater for the current oven, or you could say being less for the new oven, when in fact there is no difference in the number of defects between the two ovens. All right. So basically, given that there's no difference in the two ovens, there's a 2.6% chance that we get something saying that there was the new oven had fewer defects, right? Very important that you always start off with the definition that shows the reader you know something, and then you put it in context. Which type of error could have been committed? Well, we rejected the null, so the only type of error that could have been committed is a type 1 error. Doesn't mean we did it, but we could have committed it. All right. We could not have committed a type 2 error. So you could have, all right. So basically, that's all they asked for here. So you didn't have to put it in context of the study. You just needed to say that what happened. We rejected the null. And since we rejected, the only type of error that we could have had is a type 1. Hope that helps and hope you do really well on your FRQ test. See you around on the next one.